flow graph. In the last session also we have taken few important problems on signal flow graph and block diagram representation. So few more example problems on signal flow graphs and block diagrams will be dealt in today's session. So let's take the first example. So this is a block diagram which is given to us, and the task is we need to find the transfer function for this particular block diagram. Now the first step is, as usual, I have explained this also in the previous session. If you want to represent any of the block diagram in a signal flow graph representation, the summing point and takeoff points, that is, these points should be replaced with nodes. So replace the nodes and then start writing the signal flow graph for this. Okay, so if you can observe here, I have 1, 2, 3, 4, 5, 6, 7, 8 nodes, okay, followed by the corresponding branches. The signal flow graph for this previous example is given here. So here, as you can see, we have represented the nodes here. So totally I have 1, 2, 3, 4, 5, 6, 7 nodes. Okay, so by combining one of the node, we are able to get 7 nodes here, and these are the branches which we have connected. Now according to this signal flow graph, you can observe here that we have one forward path directly from here to here, so which is represented as G1 into G2 into G3, and another forward path we have is this one. Okay, that is G1 into G4, followed by you are finding the number of loops in this particular signal flow graph. So the number of loops can be determined like this. So one loop is, this is one of your loop. I have one loop here, and this is another loop what I have. Okay, so third loop is this loop which I'm highlighting it in blue color. This is my third loop. Next we have another loop with respect to the second forward path. So please to observe the path which I'm going to sketch now. So I'll start from this node. Okay, I'll reach like this, G4, right? Then this becomes one of my loop. So totally we are able to get 5 different loops in this, and one more loop as you can see here is, so this circle structure, that is, this circle structure is becoming one loop. So totally we are able to get 5 loops, that is 1 plus G1 into G2 G3, 1 minus G1 into G2 H1 minus G1 G3 H2 minus G4 H2 G1 and G4. So delta 1 and delta 2 is taken as equal to 1 because all the loops they touch each other, so there are no non-touching loop in this example. So by replacing all the loop values and the forward path and delta 1 delta 2 values, this is the final transfer function what we have got for the given block diagram. So similarly, let's take another example. So here also we are trying to determine the transfer function for this given block diagram. Okay, so we have one input R and an output C, right? Now you need to write the signal flow graph representation for this. So since this is a simple block diagram, we are able to get one simple signal flow graph like this. So with forward path as, so this is one of your forward path. Another forward path what I can find is, so you can go like this, take a turn to G3 and you can reach like this. So we have two forward paths which are represented as P1 and P2. One is G1 into G2, another one is G3 into G2. So as you can observe, we have two loops. So this is one of my loop, G1 into G3. Okay, so sorry, this is not the one, wait. we have one loop here. This is G3 is going in this direction, so I can have this loop, that is G2 minus H2 is one of my loop. So only one loop I am able to get, that is minus G2 into H2, and delta value is nothing but equal to, this is my delta value, so 1 plus G1 G2 into H2, and delta 1 and delta 2 is taken as equal to 1 because we have only one loop, so there is no non-touching loop here in this particular example. So finally we are able to get the transfer function for this simple flow graph as equal to P1 delta 1 plus P2 delta 2 divided by delta. So when we replace all these values, we are going to get the transfer function as equal to G2 into G1 plus G3 divided by 1 plus G2 into H2. So I hope you have followed the problem. So this is the third example which I am taking in today's session. So try to practice along with me. So this is the block diagram what we have. The first thing is you need to represent this block diagram in the signal flow graph form. So we have 1, 2, 3, 4 nodes followed by an input and an output node which you need to replace with the signal flow graph. So I have, this is my first summing point, second summing point, takeoff point, and you have another summing point here, takeoff point here, sorry, and this is your output node and this is your input node. So you have connected according to the block diagram representation which is given to you. Now the thing is you need to find the number of forward paths and the number of loops and non-touching loops. Okay, so let's find the number of forward paths first. So I'll start like this. One is direct way you can reach. This is one direction. Do I have any other direction to reach the output? Not possible. I can go like this if I try. If you try like this, anyhow this is wrong because the direction is reverse. So I don't have any other thing. So I have got only one forward path with the loop gain as G1, G2. Now coming to the number of loops in this case, here we can find how many loops. Let's check out. So I have one first simple loop here. This is one loop. It is minus G1 H1. So then I have one more loop starting from this node and ending at this node. So it is G1 G2 minus H2. Another loop is here. It is G2 G3 minus H3. So can I find any other loop other than these two? So I have got only 3 loops here in this particular signal flow graph. So P1 is G1, G2, G3, so one forward path, and I have got 3 loops, L1, L2 and L3. Now when I compare L1 with L2 and L1 with L3, they both touch either because you have the common gain among them as G1, G1. When you compare L2 with L3, you have G2 as common. So all the loops touch each other, so there are no non-touching loops. So your determinant value delta is taken as 1 plus summation of all the individual, that is 1 minus summation of all the individual loop gains. So it is 1 plus G1 H1 plus V1 G2 H2 plus G2 G3 H3, and delta value is nothing but equal to 1 because all the loops they touch the first forward path P1. So the final transfer function for this particular block diagram which is given to us using the signal flow graph representation is C of S by R of S is equal to G1 G2 G3 divided by 1 plus G1 H1 plus G1 H2 plus G2 G3 H3. So replace all the values, you'll be able to get the transfer function for the given block diagram. Now this is another block diagram. So if I see here, I have how many summing point? 1, 2, this is my third summing point. You have fourth summing takeoff point here. Fifth, this becomes your fifth node, and this is your sixth node and seventh node. Okay, now represent this using the signal flow graph. Okay, so R of S, so two summing points are combined here and it is taken together. Okay, so here also the two summing points which are together is combined and taken together, and here the takeoff point is combined with the summing point in the form of a node to simplify the signal flow graph. Now if you can see here the number of forward paths for this particular example, so it is almost looking similar. So you have G1, G2, G3, it's going like this, and G4 which is going like this. So this block diagram is also similar to the first one. So one loop here, one loop here, we have another loop here. Okay, one more long loop is this one. Okay, so and one more is like a circle. So totally we are able to get two forward paths, that is G1, G2, G3 and G1, G4, 5 loops with the loop gains as listed here. This is almost similar to your first problem, and there are non-touching loop because all the loops they touch each other. And you are going to get the transfer function by summating all the values and replacing it in the transfer function notation. So here we are taking an example of multiple inputs. Okay, so the task is to find the transfer function C of S by R1 of S and C of S by R2 of S using signal flow graph representation. So two inputs are given to us here. One is here you have taken it as R2 and here it is R1. So when I am finding the first transfer function, that is C of S by R1 of S, you are supposed to take this as equal to 0, and then you have to write the signal flow graph representation for this. Okay, let's try. Now when you take your signal flow graph representation for the block diagram, it comes like this. Okay, so here I have the second input R2 and the first input R1 which are connected. Now for my evaluation purpose, I need to consider this as 0 if I am finding C of S by R of S. So if you take this as equal to 0, okay, then we will try to find the forward paths for this. So one direct forward path is this one. So your P1 is G1, G3. Now coming to the loops, okay, so this is one loop what I have, another loop is here, you have one more loop starting like this and you are ending at this point. So one forward path and 3 loops, and all the loops they touch each other. So for this particular example, your P1 is G1, G2, G3. We have 3 loops, minus G2, H1, minus G3, H2, minus G1, G2, G3, H1, and there are no non-touching loops. Okay, and delta 1 is also equal to 1. So this is what I told you. When you are finding the transfer function C of S by R1 of S, you need to take R2 as equal to 0. Now replace all the values by determining the delta value. So delta value is nothing but equal to 1 minus summation of all individual loop gains. So it is 1 plus G2H3 plus G3H2 plus G1, G2, G3H1, and delta 1 is equal to 1 because all the loops they touch the forward path. And replacing all these values here in the standard form, we are going to get this transfer function as equal to G1, G2, G3 divided by delta value, that is 1 plus G2H3 plus G3H2 plus G1, G2, G3H1. Now this is for the first case. Now coming to the second part, now I need to make my R1 as equal to 0 and then I need to evaluate my signal flow graph. Okay, when you take your R1 of S as equal to 0, your signal flow graph will give the forward path like this. P1 is taken as G3, L1 is taken as minus G3H2, L2 is minus G3H1 G2, and L3 is minus G2H3. The non-touching loops are 0 and your delta value is nothing but equal to 1 plus G3H2 plus G3H1 G1H2 plus G2H3, and delta 1 is one of the loops, it does not touch this forward path, that is G3, so it is 1 plus G2H3. So by replacing this value, you are going to get the transfer function in the standard form, which is given as G3 plus G2H3, G2G3H3. By taking G3 common, you can rewrite this as G3 into 1 plus G2H3 divided by 1 plus G3H2 plus G3H1 G1 G2 plus G2 H3. So this is for the second input R2 with R1 as equal to 0. Okay, so this is also one of the important problem which is usually asked in your examination. Try to practice this. For the signal flow graph which is shown in the previous slide, the number of forward paths here is given as P1 equal to G1, G2, G3, P2 is G1, G7, G6, P3 is minus G1, G7, H1, G8, G3, and P4 is taken as minus G4, G8, H2, G7, G6, P5 is taken as G4, G5, G6, and P6 is taken as G4, G8, G3. So totally we are able to find 6 forward paths followed by 3 loops. So L1, which is a simple loop with a gain as minus G2H2, L2 is having the gain as minus G5H1, and L3 is having the gain as G7H1, G8H2, and we have two non-touching loop, that is L1 does not touch L3, so we are multiplying the gains of these two loops, which is taken as G2, G5, H1, H2. So for this particular problem, we have got 6 forward paths and 3 loops followed by 2 non-touching loops. So I am determining the delta value using the formula as 1 minus summation of all the loop gains. So this is the summation of the 3 loop gains, so which is added with the gain of 1 non-touching loop. So, and we have 1 forward path. So G5H1 is not touching the first forward path, that is delta 1 is taken as 1 plus G5H1, and delta 2, delta 3, delta 4, delta 5, 6 touches all the loops, so they are taken as 1, and delta 5, that is fifth forward path, does not touch the loop G2H2, so delta 5 is taken as 1 plus G2H2. So replacing all these values, we are able to get the transfer function which is given like this. So please note down the transfer function. So this question is usually it is asked for 8 to 10 marks. Now coming to the last part, here the reference books are listed. So in this module we have discussed about various important concepts. So let me just give a brief content of module 2, because we have come to the end of the module. So in this module we started with block diagram representation for the given control system. Then what is the importance of this block diagram you have learned, followed by simplification of block diagram using reduction rules. So where we have discussed about 6 to 7 rules which are used for simplifying the block diagram and obtaining the transfer function for the system. So and the most important factor that we need to consider in the block diagram representation is simple block diagrams can be very easily reduced using the reduction rules, but when we come across a complex block diagram, it is very much tedious to apply the reduction rules to evaluate the transfer function. To solve this problem, next we have taken another technique where block diagram were represented using the signal flow graph. So this signal flow graph, as you know, it was introduced by Mason, and the formula that is used for evaluating the transfer function of signal flow graph is termed as Mason's gain formula, and we have used this Mason gain formula to find out the transfer function for the given signal flow graph, and you have learned how to represent the signal flow graph for a given block diagram and how to evaluate the transfer function. So you are going to get one full question from this module. So just try to concentrate on reduction rules and problems on block diagram representation followed by signal flow graph representation. So this is the overview of your second module. I hope all of you have followed. I hope today's session was informative and interesting. Thanks for your patience listening. Have a nice day.